Hey gang, Math 5500. Gonna pump the brakes a little bit here. I want to regroup. I got into dummy variables previously, and that was actually the intent of this video. But as I was thinking through what I wanted to teach in the illustration of dummy variables, there are a few things that I want to teach beforehand. So let me give you a little indication of what's going to happen in this video. You're going to see a lot of familiar stuff, but you're also going to see some things. I'm going to introduce some things that you haven't seen before, like equal variance of residuals, and again, so hang with me. There'll be some new things that I introduce here too. Speaking of introducing new things. I am introducing a new data set. We're getting away from body fat, so yeehaw. And you'll see I'm going split screen because I'm going to need to go back and forth. So first of all, let's just let's predict the read score from LSS and IQ. All right. So first of all, obvious stuff. Okay, we get a lot of good stuff here, don't we? First of all, we get information about our intercept. Let me start at the top. I really haven't talked a lot about this line right here. This is the 5-number summary for our residuals. It gives us a good indication if we have any influential cases, any residuals that are outliers. The easiest way to determine that, I guess, is just to do a box plot of your residuals, which is super easy. Next thing I get into is I get into my coefficient box, and although the intercept is there for a reason, it does play a role. The estimate, the standard error, the test statistic, and the p-value aren't that interesting to me. Next thing I do is I get into my two predictors. Turns out that LSS is not a statistically significant predictor of read. The estimate for the beta coefficient is 4.72, standard error, test statistic, p-value 0.12. Turns out IQ is a statistically significant predictor at the 0.01 level. Now, the estimate is 0.80. Standard error is given, and our test statistic 2.93. Again, p-value 0.00682. Now let's talk about what does this mean, because again, I think redundancy is sometimes good. So to interpret the IQ line, I would say that controlling for LSS or keeping LSS constant, we would say for each additional IQ point, the predicted reading score increases 0.80 units. Get on down, we get our residual standard error. We should know what that is by now, sum of squares error. And we have a multiple r squared and an adjusted r squared. Remember, once we transition into the multiple regression family, we refer to the adjusted r squared. So we would say that 28.96% of the variance in read is explained by the regression on LSS and IQ. Down here we transition into our Anova model. So our Anova model gives us something kind of goofy. It gives us, it doesn't give us a regression line, and I've talked about this before. It breaks it down per predictor. Well, I'll tell you what, let's just take a look at it. All right, so if I look at Anova, my model, you can see that I prefer these two lines be combined to give me a a regression line, you know. But the great thing about it is, you know, we have different F values for LSS and IQ, and if we combine those, we would get this line right here. We would have, you know, 1 + 1 degrees of freedom, 2. Our error term is still going to have 27 degrees of freedom. So the p-value for the model itself, the total model, would be 0.004. So statistically significant at the 0.01 level. So we actually get that. There's a way of, if I don't know, if you want to do this kind of stuff, you can. Let's just call it model 0. What we could do is we could just predict, how do I want to do this? Okay, we could just predict read. Just look at the intercept model. Oh shoot, I'm losing my mind. And then we could do an Anova comparison of my model 0 with the model that I created up here. You get, I don't know, you know, the first line you get, and this gets into some stepwise stuff that I'll talk to you much more about in another class. But you know, we get into this line right here, which you can see has 2 degrees of freedom, a 2 and a 27, and it has a sum of squares, has our F value, which is 6.9108, corresponds to what we get up here, and of course the p-value is the same way. So there's a way of getting that in a certain form, but you know, is what it is. To me, the important thing is, can you pull out the sum of squares and the mean square for the regression? Well, you should be able to do that. The sum of squares for the regression would just be this number plus this number. The mean square for the regression would just be this number plus this number. The F statistic can be found from this line. The degrees of freedom can be found from this line. And the p-value, if we crunch those two together and create just one line of the regression, it is the p-value. Again, nobody said this is going to be easy, but that's, again, a pathetic reference to P90X, but oh well. All right, where do we go now? All right, so next thing I may want to do is I may want to look at the confidence intervals for my model, and again, notice that LSS contains 0, so just validating in a sense that we do not have statistical significance at the 0.05 level. Notice IQ is this. Now, how would we interpret IQ? We would say there is a 0.95 probability that this interval contains beta for IQ. So the population beta coefficient for IQ. So it looks like it's somewhere between 0.24 and 1.36. Let's move in briefly to a little bit of diagnostics. Now, what I'd like to do in checking diagnostics is I'd like to check the equal variance of error assumption. And we're going to get into more diagnostics on that in 6500, but I want to touch on it a little bit here. It's my approach to learn the technique and then get into the diagnostics. A lot of people say, well, you should study the diagnostics earlier. A lot of people are in my camp, and they bring it in later. So, you know, who knows who's right? I don't think either one's right. I think it's just a style. So a couple of graphs that I can create that will be helpful in making this assessment is I'd like to create a scatter plot of my residuals over my predicted values, and those will serve as my x. Well, residuals are super easy to find, right? So I can get just do my predict first. So I get my predicted values from fitted, and then I can get my errors from just taking my observed, which in this case is read, minus my predicted. So my observed minus my predicted. Now what I can do is I can look at the predicted over my errors. And what I want to see here is I want to see what I describe as a shotgun blast. Right? I want to see just randomness, utter chaos, if you will. No discernible pattern. And also I want to see, for the most part, do I have equal variance across my x levels? In other words, are these lines about the same? Well, not bad, not bad. I've got these points out here and this point down here where I have no variation there, but I just only had one, I had one prediction at approximately 31 and about 90. But I don't see any fanning. I don't see any tails to the right, tails to the left. I don't see any U-shaped. So in testing the equal variance assumption by the eyeball method, I would feel comfortable with assuming confirming, I guess, that the assumption is met. So all right, so I feel from the scatter plot, in other words, random, no patterns, no discernible patterns, that the equal variance assumption for our errors is met. Next thing I'd want to look at is normality. And there's something called a QQ plot where I can look at the, so let's examine normality of our errors. So something I can do is create a QQ plot. And first thing I need to do is create my standardized residuals. R has a nice feature to do that called R standard. We have a large data set here, don't we? Well, not too large. I don't even remember. Let's see how large it is. All right, so small data set, about 30. So I could get my standardized residuals. Now, what I want to do now is I want to create a QQ plot, and I do that using a function QQNorm for my standardized residuals. And I want a QQ line on it. Now, let me tell you what's going on here. If the normal distribution assumption is met, our theoretical, our sample quantiles versus our theoretical quantiles will match. In other words, these points won't deviate much away from this line. Now, what's deviate much? What's the line in the sand? It's really not well defined. But if I get points that fan, if you'll watch my mouse, fan quite a bit away from the line, then I start to suspect my normality assumption. I think these are relatively close. I have a little bit of concern for this part right here. No concern at all for this part. So from the QQ plot, I am going to assume I'm going to assume that our errors came from a normal distribution. Now, another way of doing that is to look at a histogram of our errors. I think that's what I called it, right? Why can't I find that? Yeah, errors. Looks like it came from a normal distribution to me. Another thing I may want to do is look at a box plot of the errors to see if there are any outliers. Ladies and gentlemen, I think we have a very symmetric distribution there. The median is almost smack dab between Q3 and Q1, and the tails that go down to the very minimum all the way up to the maximum, they seem symmetric, a little bit below -40, a little bit above +40. If I'm writing a $2.5, $3 million grant, and my grant results depend on having symmetric errors, I'm doing cartwheels because I think that assumption is clearly met. All right, cool stuff. Now let's move into doing some predictions. Now, okay, let me pump the brakes a little bit. What's really going on with the Anova? How do we contrast the Anova output with the coefficient? Well, what this part up here does, the output of the coefficient, that allows me to dive into each predictor and find if it has statistical significance, if it's a statistically reliable predictor of our dependent variable. The analysis of variance table is more of a model diagnostic. In other words, it is looking at the model as a whole. So that's why I prefer in the model to look at it in terms of the regression over the errors and, of course, the total. So have the sum of squares, degrees of freedom, mean square, regression and error, and of course have our F and our p-value. But what's really being tested here? Well, what's being tested here in this case is that the beta 0, the beta for LSS, and the beta for IQ are all equal to 0. So that's the default. We're assuming that the slopes, each of these coefficients, is equal to 0 unless we can find evidence otherwise. Well, the evidence otherwise would be in the H sub A. Would say that at least one of the B sub i's that are stated in the null hypothesis is not equal to 0. So again, we run our Anova, we get a p-value of 0.003, so we reject the null, and we conclude that at least one of our predictors is not equal to 0. So then we would want to dive into the coefficient table and say, well, at least one isn't equal to 0. Which one is it? Well, drum roll please, or lack therefore of drum roll. We know it's IQ. So we found a statistically significant model analysis through our Anova because of that predictor. If that predictor hadn't been statistically significant, then our Anova wouldn't have been statistically significant. Okay, let's move into matrices. All right, and ultimately, what I want to do here, the game plan, is show how to predict a mean response with multiple regression. And the beauty of it is it's exactly the same way it was with the with simple linear regression. Same command, same, and so it works out very nicely. So the very first thing I'm going to need is I'm going to need my mean square error. I'm going to cheat a little bit, right? So the mean square error, if I go back to my Anova table, is going to be 386.3. Next thing I'm going to need is I'm going to need my my design matrix, my response, and so on. So let's just create those. It's going to be a long video. Sorry, probably should have put it up in two, but I'm on a roll right now, so I'm going to keep with it. So we're read in row. I think, what do we say? 30. Yeah. Again, this should be tattooed to the brain. Should be pretty easy for you to create. Ones. Lots of different ways to get your ones. This is just one way. So our predictors were LSS, IQ. In row is equal to 30, and in column, of course, is going to be equal to how many predictors do we have? Oh, well, again, how many coefficients are we estimating? So that's our design matrix. The next thing we want to do is create our coefficients. So I need so notice that they align with what we have up here. That's always good. Be kind of goofy if it didn't, right? So now what I want to do is I want to move in. I'll tell you what. Let me go ahead and just do a few other things since I have this stuff created. So I'm going to create my predicted Y. My predicted Y is just my design matrix times the beta matrix. The predicted Y's are there, and of course the errors using matrix operations is just Y minus predicted Y. All right, cool stuff. Thought we had something around 44. Oh, okay, there it is. I thought we had a error around 40. Oh, we do. Okay, never mind. Okay, now the next thing I want to do is I want to transition into making predictions. Let's predict the mean. I don't know why, but I keep forgetting when it's LSS, right? No, read. Now, since we're doing the mean, we need to have a data point from the data set. So I'll go back up and look at LSS. So let's just say 8, and the IQ is, I don't know, 116. All right, so the very first thing we need is our variance covariance structure for our betas. So variance covariance for B. So I should know by now that that's the mean square error times this. Oh. Now, what does all this mean? Well, the diagonals are the variance. So we have first column for beta 0, second column for beta 1, which is LSS, third column for beta 2, which is IQ. So I know that the variance for LSS is 8.67. So if I take the square root of 8.67 48889. I get 2.945. 2.945 is exactly the standard error for LSS. So again, variance covariance, right? The diagonals give me the variance, the standard, well, I'm sorry, the square. Okay, slow down, Douglas. The variance, the diagonals give me the variance, and the square root of the diagonals give me the standard error. What do the off diagonals give me? Well, that gives me the covariance between B0 and the beta for IQ. Now, next thing I'm going to need is I'm going to need to create my XH, if you will. So my matrix here is I'm going to need a 1, and I'm going to predict 8, and I'm going to predict 116 for the IQ. So I'm going to predict the read when, again, this is for my intercept, the 8 is for my LSS, and my 116 is for the IQ. In row is going to be equal to 3. In column is equal to 1, and by row equal false. So XH we have 1, 8, 116 for obvious reasons. Now we get the transpose of that, which we're actually going to use. Now if I want to get my predicted y hat, all I have to do is put in the transpose of XH and multiply by my beta, of course. So the predicted read score is 74.60. Well, that kind of makes sense. A little bit, because if we look at what the person with an 8 received, this one received an 82. And the person with a 116 a 75. So, you know, the fact that it predicted a 74 using our model is, you know, not something that leaves us shaking our head. Now, so we want to create a 95% confidence interval for the mean read. Now I've gone, you know, completely ad nauseum or repetition overload, if you will. Confidence intervals have 3 parts, don't they? Our estimate, our critical value, in this case it's our t critical value, our standard error. Well, let's create the standard error first. We've already got the estimate. The estimate is 74.61. The t critical, I'll tell you what, let's get it. So the t critical, we're going to use QT, and we know that we have 0.025 in the left tail for reasons that I've explained again ad nauseum. But now I need my degrees of freedom. Well, think about it. To make this prediction, I have 3 estimates that were made. Where is it? I have 3 estimates that were made. An estimate of beta 0, an estimate of the beta for LSS, and an estimate of the beta for IQ. All right. So I'm going to need degrees of freedom n, which is 30, minus 3. I have 3 degrees of freedom because I had 3 estimates. Now, typically I wouldn't put 30 minus 3 there. I would put 27 there, but I wanted to write it out like that. So, you know, let's just call it a teaching moment. Sorry, I'm losing my train of thought. Okay, what else do I need? I need the variance. Well, the variance, the predicted, let me write it down over here. It's one of those things that we should have tattooed to the brain by now. So I need this. So I need transpose XH. What did I call that? Variance, covariance for beta. So the variance for the predicted is this. Well, quite a bit of variance. So anyway, it is what it is. So we're going to need the standard deviation, and let's just call it the standard error. So it's going to be the square root of the variance for the predicted y. So let's dive in. So what do we have? These three parts that we're looking for. What did we call them? Well, we called this the predicted y hat. I called this the t critical, and I called this just the standard error. So I need the predict y hat minus the t critical times the standard error. Hit my up arrow to bring the line down, just change that to a plus. So hold on, that makes no sense at all. What's going on here? Oh, okay, T critical. Yeah, I have to do, I'm like, wait a minute, the lower bound is bigger than the upper bound. So what I did, because I'd looked at the bottom tail, the T critical at the bottom tail, so what should go in here, I was losing my mind. What should go in here is the opposite of that, so it should have been 2 point, whatever it was. Yeah, we didn't even look at it, so whatever that turned out to be. Yeah, okay, crazy. So the 95% CI for the predicted mean LSS, or read, using LSS and IQ as predictors. Specific to LSS equal 8 and IQ equal 116 is 58.8 to 74.6. Sorry for that in the end. I got yeah, I was like, it makes sense. Okay, I see what it is now. All right, got more, but I think this video's already gone on long enough. I'm going to stop the video now, and we'll get into the other remaining stuff in the next video. Take care.